Okay, good morning, ladies and gentlemen. We're on to the second half of chapter 4 here, linearization and differentials. The main thing we're going to work with today is just the linearization in the beginning here. We'll work more with differentials tomorrow. Little review, not really a review, this totally plays into everything we're doing today, but find the equation of the line tangent to f of x equals x squared minus x minus 3 at the point x equals 2. Well, we've done this quite a bit of times this year, I believe. And in order to find equation of a tangent line, we need a point and we need slope, right? And the point, well, if we need it precisely at x equals 2, well, we're going to find the point f of 2, which is going to be what, 4 minus 2 minus 3, which that's going to end up equaling what, -1? So we have a point of 2 comma -1. And then our slope, because we're all calculus students, we know the slope comes from the derivative. So f prime of x actually equals 2x minus 1. So the slope at x equals 2 is actually f prime of 2, which is going to be 4 minus 1, which is 3. So we know the slope is m equals 3. And once we have the point and the slope, well, we know we can just use our y minus y1 equals x, our m times x minus x1. So we can quickly write our equation of the tangent line, which is y plus 1, because it's minus -1, equals the slope times x minus 2, okay? And a lot of times, when we want to graph this, we're just going to subtract that 1 over and call it 3 times x minus 2 minus 1, okay? Well, what's this whole big deal with tangent lines? We hear lots about tangent lines. Well, we're finally going to get an application of a tangent line today. We're not just going to write equations of tangent lines. They're used, okay? And tangent lines, we use them to approximate values of functions, okay? And you might be looking and say, well, why would I want to do that? Because I can just plug the number in. Well, we're using the tangent line to approximate particularly ugly values within particularly ugly functions. And why would we want to do that? Well, if I think about this, isn't it easier to evaluate a linear function than it is to evaluate a quadratic function, especially when decimals and ugly things are involved, okay? And it's a really special thing. So this is the equation of my line, okay? This is the equation of the line tangent to f of x at x equals 2. And what that does is that does something really special. And it does something so special, it actually has a special name. And what this actually is it's called the linearization . It's the linearization of f of x at x equals 2. Well, what the heck do you mean by that? Well, bottom line is if I had a parabola, say this is my f of x, okay? And bottom line, I know my slope here is 0 at my vertex. And bottom line, if I'm looking at my derivative at 2, if it's 3, I know for sure that point is going to be to the right of my vertex because I have a positive slope. So my equation, my line tangent, let's say it's like right here. Bottom line, if I zoom, and I zoom in really closely on my tangent line, what happens is the line becomes the function when I'm very close and when I'm within a reasonable proximity of x equals 2. And what do you mean within close proximity? Well, if I wanted to approximate, okay, if I wanted to know what the heck is f of, oh, I don't know, 2.01. Okay, well, if I wanted to do that, honestly, that's a pretty tough calculation inside the function. But if I'm within a reasonable neighborhood of 2, okay, this I can approximate, I can plug 2.01 into my linearization function. I don't need a calculator or nothing to do it. It's actually really easy, and I can approximate it very quick, okay? And it's called the linearization. Well, the linearization actually has a special name in calculus. Linearization they call L of x, okay? And L of x, it's just another way to say find the equation of a tangent line. If they say find L of x, find the linearization. Hey, that means find this function L of x, and L of x, it actually equals 3 times x minus 2 minus 1 at x equals 2. That's my linearization. Because if I zoom into my box over here, okay, and I continue to zoom in on that point at x equals 2, the closer and closer I get, every point really close to 2 behaves exactly like that line within a reasonable error factor, okay? And if I think about this linear, calculus has confusing ways to write things. And if I'm thinking of my linearization, if I'm thinking of my tangent line, y equals 3 times x minus 2 minus 1. If I think about all this stuff, okay, it's a tangent line. So what happens is y is my approximation. My y is my L of x. Well, what the heck is it? What's that 3? Where did that 3 come from? Well, that 3 is really f prime of 2, isn't it? It's the derivative at my special point here is x equals 2. And what that's x minus 2. Okay, well, that's at the point 2, I can see. And what's that minus 1? Well, that minus 1, where did that negative 1 come from? Well, that came all the way up here. That's when I put, oh, negative 1, that's the same as f of 2. So that's minus f of 2. So what this is a linearization, okay, of f of x at x equals 2. I can approximate f of x anywhere within a reasonable proximity of 2. I want to be close to it, and I'm going to get a really good approximation of any decimal value close to 2 just by plugging it right into that double right there. These two are not basically, they are the same thing, okay? Because when I'm close to 2, that's what happens. Well, this is the linearization at f equals 2. Notice my 2 is everywhere. Okay, I can tell I'm linearizing my function at 2. Well, if I turn the page here, this is my linearization of f of x at x equals a. Check it out. This is my slope anywhere, okay, anywhere, and wherever my anywhere, that's my a. So that's like my f prime of 2 before. My times x minus my point plus f of my point, and I can approximate my function anywhere. Well, what are these 3 asterisks here for? Well, these 3 asterisks are basically here saying L of x actually equals f of x at x equals a. Okay, because that's actually at the point of tangency. So L of x, the linearization of the function at the point of tangency, they are exactly the same thing. We should be able to picture that real easy because there's my point of tangency. The function's the exact same value as my tangent line. Okay. Well, what's the second asterisk for? Well, the second is because it says my linearization or my tangent line function is approximately equal to f of x. It's almost the same as f of x at any point that is almost equal to a. Okay? So when I'm close, when x is close to a, my linearizing function is close to the same value, very close to the functional value. Okay, and the third one, this is my application part. Okay, this is where we're looking here. We use L of x to approximate values of f of x at close values to a. Okay? Why do we want to do that? Why do we want to do that? We want to do that because L of x, our linear function, is easier to work with. It's easier to make the mathematical calculations. Okay, very easy. And you're going to say, what is this? Well, it's actually the foundation of differential equations. Well, we'll find a little bit more of those out. It's a lot of stuff with the second half of the semester. Okay, but that's what we're going to do. So let's just do a couple examples here. So if I looked at my next one, okay, we want to find L of x for f of x at x equals 8. Well, that's saying find the equation. This right here, find L of x, means find equation of line tangent to f of x at x equals 8 in this case. Now notice, this is a mouthful. It's a lot of stuff to write. Mathematics, we have shorthand for lots of things. So L of x is a tangent line to the function at that point. Well, what do we need to write an equation of a tangent line? Well, real easy. We need a point and we need slope. And we're going to see why we want to do this. Okay? Well, the point. Okay, well, we need to find what the heck is f of 8. Well, f of 8 is the square root of 1 plus 8. So it's 3, so we're at the point 8 comma 3. There's our point. Well, we need the derivative. Well, remember, we're going to look at this guy as 1 plus x to the 1/2. So when we find that derivative, we're going to say f prime of x actually is going to equal 1/2 times x plus 1 to the negative 1/2. Don't forget a chain rule. Oh, 1 plus x, I'll write it the way it is. It's equivalent, doesn't matter, but I have 1/2 times 1 plus x to the negative 1/2. Don't forget your chain rule. It's just 1 in this case. So my derivative is actually 1 over 2 square root 1 plus x. Well, what does that mean? My slope is f prime of 8. Well, that gives me 1 over 2 square root 1 plus 8. Well, that's 1 over 2 times 3. That's 1/6 is m. Okay, so we can use that to approximate it with the slope. So what is my L of x function? Well, my linearization function, and if I be honest with you, I never wrote them straight out like they do. I always went, oh, y minus 3 equals 1/6 times x minus 8. And then I said, okay, I solved it. X minus 8 plus 3. And then I always came back and I said, oh, that's right. They wanted me to call it my linearization function. So that's what I did. Okay. Well, why do we want to do that? Well, because if we want to approximate f of x, we want to approximate it close to 8, 7.8. All right. So is it easy to take the square root of 8.8? Not really, in my opinion. Okay. So that's why we have our linearization function. We are going to say my approximation at 7.8 is going to be 1/6 times 7.8 minus 8 plus 3. Well, what the heck is 7.8 minus 8? Well, I guess that would be what? 1/6 times negative 0.2 plus 3, right? Negative 0.2. So what I do is I'm like, okay, well, I know what negative 0.2 is as a fraction. That's negative, what, 2/10? Wouldn't it be? Which, when I simplify that out, that's 2/60. So that's really, what, 1/30 plus 3, negative 1/30. So that's actually going to be 2 29/30. Pretty close. And if I wanted that as a decimal, that's about 2.966. I'm going to throw another 6. They keep going on right there. So I can approximate it. Well, what is f of 7.8? Well, that's actually going to give me the square root of 8.8, isn't it? And the actual square root of 8.8, it's 2.96648. Well, check it out. Those are really super close, aren't they? As a matter of fact, they're so close, they are within 0.00019. Is that an error factor that you could live with? Is it easier to get this than it is to get this over here? Now, I know some people are going to argue and say, I'm really good at estimating, and you're right, but this isn't elementary. This is a basic example, not a super ugly function, and you've seen some bad ones, okay? So let's try another one here. This other one's not in your notes, so what I would like you to actually do is, why don't you just try to find L of x that says find the equation of the line tangent to the function that x equals negative 4. Why don't you give it a shot? Hit pause, see if you can come up with it. Again, we need point and slope. So we need to find what is f of negative 4. Well, f of negative 4, well, that's going to be what? 16 plus 9, well, that's 25, so that would be 5 now, wouldn't it? So our point is negative 4, comma 5. Well, let's remember this is x squared plus 9 to the 1/2. So we need to find our derivative first, f prime of x. Well, that's going to be 1/2 times x squared plus 9 to the negative 1/2 times my chain rule of 2x, which means that's going to be, notice my 2x is on top, my 2 is on the bottom, and I have that square root of x squared plus 9. And I can see that in my reducing here, this little guy is going to go away. Those reduce out, so there's my derivative, f prime of x. So if I need my slope, I need to know what the heck is f prime of negative 4. Well, f prime of negative 4 is going to be negative 4 over the square root of 16 plus 9, which is going to be what? Negative 4 over 5, I believe. That's my slope. And that means, okay, ugly function. That means what I'm doing is I am linearizing my graph really close to negative 4. So if I wrote it, I would say Kruger method is y minus 5 equals slope times x plus 4, which means then I would say L of x, because they want me to call it my linearization function, negative 4/5 times x plus 4 plus 5. And I can use that little bugger to approximate that function when I'm close to negative 4. And if I needed to do it, let's say I needed to do it at, I don't know, 0. Well, obviously we wouldn't want to do that, but if I wanted to do it at, let's say I wanted to approximate what x equals of 0.01. Okay, well, that's not going to be super easy, but I could linearize it when x equals maybe 0. I could find my slope at 0 to find all this good stuff and make an approximation of it. Okay, so that's all we're doing right now, and for the time being, they are telling us where to linearize the function. And I think I have one more here that is also not in your note pack. So what we're going to do is let's approximate what the cubed root of 26 is by using linearization centered at an appropriate nearby number. Well, how would we think about doing this? Well, first and foremost, hopefully it's obvious to you that our function is the cubed root of x. And I would want to find the perfect cube closest to that. So I would say at maybe x equals what? What are we going to go after here? Maybe 27, because I know how to do that. So I could find my point, and I could find my slope. Not slope. So f of 27, it's 27. Well, that's saying what's the cubed root of 27? Well, we know that. It's 3. So I get the point 27, 3. Okay, because we know. So we know we're going to be a little bit less than 3, hopefully, because we're under that 27. Well, let's look at that as x to the 1/3. So that means we need our f prime of x. Well, that's just going to be 1/3 x to the negative 2/3, right? Which is 1/3 cubed root x squared, isn't it? So, well, what's my slope? Well, that means my slope is going to be f prime of 27. If I'm linearizing at x equals 27, that would be a realistic point. 1/3 times cubed root of 27. Remember, we would want to throw the squared outside. That's going to give me 1/3 times, well, the cubed root of 27, well, that's 3, and I got to square it. So that's 9 times 3. That should give me a slope of a 27th, shouldn't it? 1/27, that's my slope. Okay, so if I had to approximate this guy, I would find my equation, my tangent line quick. Y minus 3 is 1/27 times x minus 27. So I would say my linearization model is going to look like this, plus 3. Then what I would do next is I would say, okay, let's approximate what 26 is, because I think 1 unit away, I'm thinking we're all going to be in the same idea that 26 minus 27 is going to make an easy calculation, which is 27th times -1 plus 3. Well, that's negative a 27th plus 3, so that's 2 and 26 27ths. That's what L of 26 would equal. Okay, I think we're pretty in agreement here that that's close, and I can get that. And if I slammed it to a decimal, well, that's 2.963-ish. Okay, and if I actually came with my calculator and I said, hey, what is the cubed root of 26? Well, what does it equal? 2.963. So these are almost exact, but notice I rounded them both to 3 decimal places in this case, and we're pretty good. Good model for it. Okay. So we're going to talk about approximating another one. I believe this one is in your notepad. We're getting pretty close to being done, and tomorrow's video is going to be a little bit longer. Sorry, but we're going to find L of x for f of x at, don't worry about that x naught. That just means basically my beginning point of 1. Okay, so centered around 1 when x equals 1. Well, my point hopefully is pretty simple dimple to see, which is 1, 1. Okay, because if I put 1 in there, I get 1 out. There's my point. What's my slope? Well, my slope is going to be m equals what? Well, remember, we need to find out what f prime of 1 is. Well, to do that, we need to know what f prime of x is first. That's tough, 4x to the 3rd. Well, that's going to be 4 times 1 cubed. So looks like my slope there is going to be 4, doesn't it? So if I linearize this, I'm looking y minus 1 equals 4 times x minus 1. So I'm saying L of x is going to equal 4 times x minus 1 plus 1. And the answer is, if I really wanted to call my L of x function here, if I really wanted to distribute it out and call it 4x minus 3, can I do that? Heck yeah, they're equivalent. They're both just fine. I'm leaving mine in the first one, but they are the same. So if I wanted to approximate that, would you rather take 1.01 to the fourth power, or would you rather approximate 1.01 minus 1 plus 1? Well, that's going to be 4 times 0.01 plus 1. Well, that's 0.04 plus 1. 1.04. Is that what we're coming up with? If I approximated it at 1.04? Okay, well, if I actually type it into my calculator, I don't know. I think this equals 1.04060401. When I compare these two, rather than take this to the fourth power, especially if I didn't have a calculator, didn't need a calculator for any of that, are you okay with a 0.0060401 error? Are you okay with that? I certainly would be. It's a pretty high tolerance that we're going to be doing, and that's what we're going to be using these in some application problems to minimize or to calculate amount of change, because that's really kind of what we're doing here. We're finding amounts of change. So when I look here, okay, I think you have a little graph, and I believe you need to write this stuff down or write this stuff down, and I'm going to give you a minute to do that, and hit pause, and then we're going to create a graph, and I'm just going to describe what all this is going on, and then we're going to talk more tomorrow. Okay, I lied. I'm not going to do any more of this right now. And just make sure you have the information you see on the screen about where your graph is on your paper, and then we're going to take off from here tomorrow, and we're going to finish out the rest of this section, and then you will be game to do all your homework. So until tomorrow, have a great day.